Okay, so let's talk about calculus. I know. The word itself can sound pretty heavy, right? But honestly, at its core, it's built on some really simple and kind of beautiful ideas. Today, we're going to tackle one of the big ones, the derivative, and we're going to do it with just a little bit of intuition. I promise, by the end of this, you'll get what it is and why it's so darn useful. Think about it like this. A straight line, like a perfectly straight ramp, has one slope. It's the same steepness everywhere. Easy. But what about something like a roller coaster track? Its steepness is constantly changing. How in the world do you measure the steepness at one single tiny point on that curve? Well, that's the exact problem derivatives were invented to solve. So what is this thing, a derivative? Put simply, it's just the fancy calculus name for the slope of a curve at one single specific point. It's how we measure change at an exact instant. And to understand it, we're going to use a really simple idea I like to call the nudge. Okay, check out this graph. This is the function f of a equals a squared. It's a classic U shape, a parabola. We're going to zoom in on just one spot, the point where our input a is exactly 2. Now, if the input is 2, the output is 2 squared, which of course is 4. Simple enough. Now for our nudge, imagine we're at a equals 2, and we just nudge it a tiny bit to the right. Let's say we move it to 2.001. So what happens to our output? Well, if you plug 2.001 into our function and square it, you get something really close to 4.004. So that tiny little nudge in our input caused a little change in our output. And here's where the magic happens. We moved to the right, our run, by 0.001, and the function went up, our rise, by 0.004. So wait a minute. You notice that? The function went up 4 times as much as we moved it over. This relationship, this ratio, that's the key to the whole thing. And boom, that is the core idea. The derivative is just the slope of that teeny tiny triangle we made with our nudge. Remember rise over run from school? That's all this is. It's just how much the function went up divided by how much we moved to the right. So let's do the math. Our rise was 0.004, our run was 0.001. You divide those, and you get exactly 4. That's it. In the language of calculus, we'd say the derivative of the function at the point a equals 2 is 4. It's just the slope right at that spot. All right, let's build on this because here's where it gets really interesting. Remember, a straight line has the same slope everywhere. But a curve is different. Its slope changes. So our little nudge experiment should give us different answers depending on where we are on the curve. Let's test that idea. What if we do the exact same experiment, the same tiny nudge, but we start somewhere else entirely? What if we start where a is equal to 5? Now this is so cool. Look at the comparison. At a equals 5, our function's value is 25, right? Because 5 squared is 25. Now we give it the exact same nudge, just 0.001. The output goes up to about 25.010. So our rise this time is 0.010. You divide that by our run of 0.001, and the slope is 10. The same size nudge gave us a way steeper slope. And that's the big aha moment. For a function like a squared, the derivative, the slope, is not a fixed number. It changes depending on where you look. At a equals 2, the curve has a steepness of 4. But out at a equals 5, it has a steepness of 10. The curve is getting steeper and steeper the further to the right we go. Now, you're probably thinking doing that little nudge calculation every single time would be a real pain. And you'd be right. This is where calculus becomes so powerful. It gives us a formula, a shortcut, to find the slope at any point we want, instantly. If you were to open a calculus textbook, you'd find this little formula right here. All this fancy notation means is that the derivative, or the slope, of our a squared function is just 2 times a. That's it. This one simple expression is the secret recipe for the slope of our curve, anywhere. So let's test it. Does the shortcut actually work? Well, when a was 2, our formula predicts a slope of 2 times 2, which is 4. And hey, that's exactly what we found. When a was 5, the formula predicts 2 times 5, which is 10. Another perfect match. The shortcut works like a charm. This quote here really brings it all back home. It translates that math formula right back into our simple nudge idea. That 2a is just telling you the multiplier. It's saying for any a you pick, If you give it a little nudge, the function is going to go up by 2a times the size of your nudge. It's that simple. So let's zoom out and wrap this up with the main ideas. This whole process, this whole way of thinking isn't just for a squared. It's a fundamental concept that works for all sorts of different functions. In fact, for most of the common functions you'll ever see, mathematicians have already figured out these shortcuts. For a cubed, the slope formula is 3a squared. For the natural log of a, it's 1 over a. The big takeaway here is you don't have to reinvent the wheel. For most functions, you can just look up the formula. So here it is, the 3 things to take away from all this. Number 1, a derivative is just a fancy word for slope. That's all. Number 2, for anything that's not a straight line, that slope changes depending on where you are. And number 3, and this is the best part, there's usually a handy formula you can look up to find that slope in a flash. And that leaves us with one last big idea to think about. If a derivative lets you measure the rate of change at a single, precise instant, just imagine what you could do with that. You could find the exact speed of your car at one moment in time, the instantaneous growth rate of a population, or the precise trajectory of a rocket ship. The applications, well, they're basically endless.